I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism podcast, an exploration of the past, present, and future of material science and engineering. My name is Andrew Falkowski. I'm a student at the University of Utah, and I'm joined by my co-host and my professor, Dr. Taylor Sparks, and we are joined once again by Kate Winning from Oxford Space Systems. Previously, we did a great episode on all things textile materials, and now we're going to go to her home turf, that is textiles for space applications and beyond. Taylor, Kate, how are you both doing?
Fantastic. And this is going to be such a good episode. I can tell because I'm super excited about this one and studying for it. Kate, how are you doing?
I'm good. Thank you so much for having me again. I'm really looking forward to talking about this.
Perfect. So maybe just to start, your work, maybe you can tell us a little bit about what you do on a daily basis at Oxford Space Systems, and first how you got there from a degree in textile engineering, or is it textile engineering?
So I studied textile design,
Okay.
and my specialism was woven textiles. But then completely differently, I ended up working at Oxford Space Systems, where I'm actually dealing with knitted textiles. So yeah, I mean, I graduated from university. I honestly didn't really know what I was going to do because I probably assumed that I was going to be working in fashion or something to do with interiors, but I developed a real interest in technical textiles and working with more man-made fibers. So when the job came up at OSS, it just seemed perfect to be working with really interesting materials and applying my textile knowledge, and coolest of all that it's for space. So yeah, I think when I went there I didn't really know what to expect. I actually was lucky enough to work on multiple projects, so it wasn't all textiles at first, but then as I progressed in the company, then I became the leader of the technical textiles department, where we work on the knitted metal meshes for one of our big antennas.
So Kate, my kids are watching Stranger Things right now and they're loving it, right? And in season, 2 or 3, Dustin has this ham radio antenna and it's huge and they foist it up on this hill and it unfolds and it's really large, and that's how they're able to communicate long distances. Your average listener might have that sort of mental picture in mind. They think of an antenna. But the challenge is if you're going to deploy something like that in space, first off, having something large and getting it into space is going to be challenging. So we need it to be compact while it's deployed, when it's being sent up there, and then it deploys and it gets large. We know that weight, every kilogram that you send, every gram you send to space is painful. All of these things have to come into play, and yet you ultimately have to have an antenna, something that serves its purpose. So why are textiles the right answer for that?
So they're super lightweight, as you can imagine, and they can fold up. And that's actually the interesting challenge with deployable antennas. You've got a hard-wearing backing structure, then you've got the secondary reflector that will send its signal, and then you've got the primary reflector, which is the textile. So it's this kind of not delicate, so delicate that it will get damaged, but it is, you can imagine it's delicate against carbon fiber ribs. So yeah, it's really interesting trying to get those two opposing materials to work together and deploy without any failure or any damage to either material.
And these things have to last for quite a while, I imagine, right? It's not like you're shipping a new antenna regularly. You want this to survive the lifetime of the satellite?
Yes, exactly. So that's another thing. It's like every move on Earth that you do to the when I'm working with the primary reflectors, I've got to be very careful at all times to keep it as pristine as possible from creation to integration to the backing structure, and then has to go through all its vibration testing, survive the launch, deploy, and then last its the determined time that it's going to last up there.
Are you able to give a rough sense of scale? Like, how small is it when it's folded up versus when it deploys?
So I've actually worked on a wide range of antennas, some very small, like maybe the size of a phone box or something, a bit bigger than that, and then one that's the size of a room.
Holy cow.
So yeah, they have different purposes, but yeah, the biggest ones that I'm working on, at the moment it's 5 meters, so it's seriously big.
So you've got it's got, it's going to be vibrating like crazy. Obviously, when it gets deployed, there's G-forces, there's all that. It has to unfold and unfold correctly and not have damage from being folded in the first place. But then once it's in space, what types of constraints and materials design constraints does that introduce? Because you've got, I'm sure, thermal loading as it goes in and out of the sun's shadow. I'm sure there's irradiation concerns. Can you enumerate some of these challenges and how you have to select materials based off of those?
Yeah, so there has to obviously be a temperature requirement. It's going to be facing certain temperatures in lower Earth orbit that we need to consider. Um, and then there's also what's called the atomic oxygen protection of the material. So that protects against corrosion of the surfaces, and it's something. Yeah, there's so many considerations you have to
Wait,
deal
so
with.
it's low enough that it's still near the atmosphere that there's oxygen and corrosion issues? Am I hearing
Yes.
that right? Oh, I didn't realize that.
Yeah, if you look at some of the materials they use, you could use maybe silver versus gold. Gold is often preferred, I think, because of that corrosion resistance.
Oh, wow. Okay. I assume this was like way out in space, but it's actually close enough that we still have to worry about corrosion.
And even then, the
Yes.
temperature swings are pretty extreme. I was seeing that temperature swings can range from approximately negative 150 Celsius in shadow to positive
I
150
saw that.
Celsius in sunlight, which is a pretty major temperature swing too. So you need to somehow maintain, this parabolic shape while you're going through that, I imagine, right?
Yeah, so I mean, it's not exactly my area of expertise, the material selection, but that's what I like about working with the engineers is they have all this knowledge of the materials that we can work with, and then we kind of come together, and I explain to them how they can actually physically attach things together with sewing and other joining methods, but it's all with space grade materials.
So, Kate, are the textiles that you end up knitting together, right? Are they are they multiple like distinct fabrics that are running parallel to each other, or is it like a core shell structure where you'll have like a core of something and a shell of another material? Like, what's the actual design that they typically integrate? Because you said that there's like you have to have a conductive material, a reflective material, like the backing material. Like, there's different components. How do they get integrated?
So I suppose it would be a good time to explain what is the wrapped rib antenna. So it's called wrapped rib because it's literally these carbon fiber ribs that get wrapped around the antenna and deploy, and it's a kinetic deployment, which then leads to why we have the knitted reflector. So knitting is stretchy and it needs to be able to move with the ribs moving at quite aggressive force. So yeah, the knitted element is we use a gold-plated tungsten yarn, and we actually use a fashion knitting machine to make the what we call the mesh. So yeah, we've got the carbon fiber ribs and the gold-plated metal mesh. That's quite a mouthful. And then there's other materials. Again, I'm not going into too much detail that we use to join the mesh together. You can imagine we don't just knit out a big circle. That are space grade again, and there's various like protections around the fabric to ensure that the contact between the ribs and the mesh, like we don't want obviously it to get damaged. So it's quite a balance of having this potentially quite fragile fabric against a very hard backing structure, but that's what's so cool.
That's exploding open.
Yeah.
Yeah, that's wild. That's a hard materials challenge.
Made from a gold-plated tungsten yarn that we knit on basically a fashion knitting machine. So yeah, it's a gold-plated reflector, and it has other materials used to join it together. Again, I can't go into too much detail about that, but it's basically all the space grade, coatings and materials that we're allowed to use that will be, you know, correct for the temperature requirements.
Yeah, I was reading a little bit in preparation for this episode and wondering why. So tungsten is one option. I saw some people use molybdenum as well, like why they use these basically like refractory elements for the cables. And it has to do with creep resistance, I think. My understanding is to try to get that parabolic dish, you have to pull this in sufficient tension that it maintains its shape. But that can cause creep in the materials, which is just that slow migration of atoms to try to relax that tension. But things like tungsten and molybdenum definitely resist that. Are you able to say like what kind of diameter of fibers you're working with? Because usually we don't think of these elements as being particularly flexible when they're in a solid form.
But it does depend on the diameter, right? How
Yeah.
thin, the aspect ratio.
Yeah, so it's the gold-plated tungsten is thinner than a strand of human hair. It's very thin, so you can imagine it's quite interesting trying to knit that on a fashion knitting machine. But we've, through our expertise, we've got it to work, and now we have the wrapped rib antenna.
I have to imagine there's got to be some dialing in and some challenge there in terms of having enough tension to maintain the weave or the knit without it accidentally breaking the thread.
Oh, geez, yeah.
Like my fiance's sewing machine is constantly breaking threads. If she switches, she has to adjust the tension. Is that a similar challenge that you faced here, or is it pretty durable?
There was extensive research into how, what knit structure we wanted and how, the tension of it, and we've got our secret formula for that. But yeah, it is. You do have to be constantly dealing with the machine and getting it to do what you want it to do. Because usually in fashion knitting, it should be a case of just set it running. I mean, maybe someone from fashion would not like to hear that. It might be difficult as well, but we've got it to work how we want it to.
And then I know you can't say the specific knit you're using, or maybe you can, but what's kind of the design philosophy behind the knit that's being used here? Is it in some sense asymmetrical in terms of the tension? Like, is it tighter in some dimensions or looser in others in order to allow for that unfolding? Or is this actually just like a very standard warp knit?
I would say, so knitting is chosen because it's a kinetic deployment, so it needs to, you can imagine actually let me explain that it's the wrapped rib antenna basically means these carbon fiber ribs that are holding the mesh are wrapped up in a very specific way to deploy the mesh, which doesn't get torn or damaged in the process. And yeah, it has to be knitted so that when the ribs kind of bounce forward and backwards, the mesh moves with it. If it was woven, it would probably just rip off because it's too strong. And then yeah, the knit has it's kind of like memory. It will go back to the shape that you wanted it to be, and it will have that. There's again extensive testing into what's called the RMS surface accuracy, that will be for the requirement of the frequency that they're working with.
And then something I was also looking at is when you're trying to reflect a specific wavelength, they use this term openings per inch. Or basically like the size of your opening and the density of those openings seems to affect what kind of RF signal you can actually reflect meaningfully. This must be a fairly dense knit. And are there any challenges with that? I feel like usually knitted things are a little bit more porous, at least in the items that I have. Or is it just that the size of the fibers allows you to get, the diameter of the fibers allows you to get a pretty dense fabric?
Yeah, I mean, like I mentioned, the research that we've done has kind of determined the knit that we use, and it's we just use the same one again and again. Just the size of the wrapped rib antenna will change, so that we have to contest with size changing. Obviously, we have when you go 2D to 3D, it's different, so you can't put something flat onto something 3D, so there's a few tweaks that we have to make in order to make to go bigger.
Mm-hmm. Are there any other projects you've worked on, or have you primarily been focused on just the antenna weaving? I keep saying weaving, knitting.
Yes, there are some other projects I've worked on. I've worked on quite a few, but so I'll just mention my favourite one. It was I think, oh, I should know this, 3 or 4 meter long, what we call the helical antenna. And it's basically this kind of big spring that's almost deploys like a jack in the box. So it's really cool. And I had a really great time working on that project. And I'd say the highlight is I actually got to make a little sun hat for it. That might sound ridiculous, but basically, when the antenna was stowed, there was potential for it to get too hot as it was passing by the sun. So I designed these little panels that would act as a sun hat, and I actually got to hand sew and attach it to the antenna. And I even have a picture of it up in space now. So
Oh, that's
it's
so
really cool.
Awesome. It's cool to hear that there are bespoke, handmade materials going into space still.
Yeah.
Usually everything is just so machine controlled and precise. So it's still fun to see the hand of the creator being influencing the materials that are out there and doing real work too.
Yeah, I think that's what I find the coolest about this job is that these, weaving and knitting are ancient crafts and hand sewing as well. And it's still not been replaced somehow. I'm still every day doing hand sewing, using the sewing machine, the knitting machine, working with woven fabrics, but they all have, their coatings, like I said, for the ATOX protection and everything to make it so it can last up there.
Yeah, it's really interesting to look at the sorts of materials and techniques that are being applicable for things like space, where the manufacturing techniques are fairly ancient, like you said, but the materials are very advanced, like the textile example here, but even things like origami structures, right? This really old, just sort of like paper folding technique is now like a really sophisticated way to make structures compact and allow them to expand out in space.
Yeah. So the satellites are amazing with these antennas are very, very impressive. We were also looking at other textile applications, and I had a couple come to mind, but the one that we're going to talk about today is the spacesuit. Holy cow. If you want to go down a rabbit hole of interesting engineering, the spacesuit is gnarly. I would argue it's got to be the most sophisticated textile that humans have ever come up with. It's not Kevlar, it's not carbon fiber composites, it is the spacesuit, right? And just consider the job requirements that the spacesuit faces. We've already talked about with the antennas, the temperature, right? It goes negative 150 to positive 120. So it's boiling water on one end and it's incredibly cold on the other. But now you also have to protect against the vacuum of space because there's a living organism inside of that thing. If you normally expose your body to the vacuum of space, all of your liquids in your body boil, right? Like you absolutely deconstruct. But then there's other stuff that I hadn't thought about. There's micrometeoroids, like itty bitty tiny particles, which you're like, well, who cares if it's so small? But these are traveling at 10 to 20 kilometers per second, like insane speeds. You've got radiation, pretty amazing levels of radiation, both from galactic cosmic rays as well as what are called solar particle events. Ironically, something that I took for granted that wouldn't be that hard to design around is that these have to be mobile. It's a suit after all. You have to wear it and do things and repair things. And mobility turns out to be one of the huge major challenges of these suits. You have to maintain pressure as well as an oxygen atmosphere because you're going to be breathing it. It's not like you have a snorkel or a scuba thing attached to your face. Like the suit contains the air that you need to breathe. And then lastly, you have to manage your sweat, CO2, your body heat. Picture like the still suit in Dune, right? The sort of science fiction. Like how do you make that a reality? Like this is hard. Really, the better way to think about the spacesuit is it's not a spacesuit. It's not like clothing you wear. It's better to think of it as a mobile spacecraft. That's really what you're building with these things. And obviously, there's no single textile that's going to cut it. This is definitely going to be a job for a composite. It's going to be a multi-layer composite. In fact, when I was doing the research on this, it reminded me of our episode 108 on food packaging when we talked about Tetra Pak, which was like a paper backing. And then you've got like the oxygen barrier and you've got the gas barrier layers. Like we're going to have a similar thing. So when we think of the challenges that I listed for the spacesuit, we have material solutions for each of them, right? So you have to have vacuum pressure. Therefore, the solution is that we're going to have some type of pressure bladder that you're going to be inside of in the suit. Mechanical mobility. Okay, If you just have a pressurized bladder, it would blow up like a balloon. That's not what we want. That would not have any mobility. So there has to be like a constraint layer that's holding that pressure in. Those have to, like, the separation of those two things was one of the real innovations of the early spacesuit. Like the pressure containment and the restraint are different systems.
Probably also to distribute that pressure, right?
You want it even, right? Yeah, this can sort of contain that evenly so you don't get pressure points where it spikes or anything. You've got thermal control, which is going to come. The solution there is going to be obviously some type of insulation. They rely on a multi-layer reflective insulation. And then
yeah, it's aluminized mylar. So space blankets, basically.
Space blankets, yeah, like several layers. You got to have impact protection, though, if you're getting hit with these little micrometeoroids. So you're going to have something that's high strength. You're going to have high strength fibers. And then you have your radiation. You have to reflect that high radiation with some sort of reflective layer. So taken together, modern spacesuits have something like 14 distinct layers. I'm wearing like a single knit shirt right now, right? An undershirt underneath it. Even that feels kind of like a little bit restrictive. Imagine now 14 layers, and now you have to do complex engineering tasks.
You have to move, which is a challenge, right? Because as you move, right, like you could imagine the volume changing, which changes the pressure internally. And
Absolutely.
So there was a lot of work that went into designing different joints and ways of allowing people to move as they want while keeping a constant volume. I think the gloves are really insane.
Dude, the gloves are the
dexterity.
hardest. Yeah. And here's the catch, we'll get to it, but let's start with the early spacesuits. So if you go back to the Apollo missions back in the 70s, these were much simpler than what we have today, but it's the same basic principle. They had a nylon inner liner, which was comfortable, and it served some other purposes. For example, it has to be flexible. It has to have good fatigue resistance. That's where most of your movements are happening, so it can't become brittle over time as you move that joint. Then for the bladder, to hold the pressure, they used neoprene, but they coated it on top of nylon. And then to restrain that bladder layer, the structural component, they used polyester. And they used Dacron is the fiber name, but it's a polyester basically. And then for the insulation, it was mylar, which is really just almost the exact same as PET. If you actually look at the structure of polyester, which is PET, polyethylene terephthalate, and mylar, it's almost the exact same. Basically, it does have an ethylene group on the end, and it's stretched a little bit. And because it's stretched, you can aluminize it because it's partially crystalline, whereas PET isn't, but it's almost the same material. And then interesting, the outer layer for the Apollo 13 missions where they actually went to space, this was what they call beta cloth. And beta cloth is when you take fiberglass and you impregnate it with PTFE. And there's a specific reason they did that.
Yeah, why?
It's fireproof. And if you remember the history of space, I don't know if you've seen The Right Stuff or Apollo 13, Apollo 1 had these astronauts die in a fire. They got trapped inside the vessel because it was bolted on, and the hatch actually opened inwards and the pressure building up inside. They couldn't get out, and they actually were incinerated. So on the engineer's mind was thinking about how they could make these sort of fireproof. And so this PTFE fiberglass coating was the outer strong layer. And again, the main thing we learned from the 60s and 70s when they were doing this was the separation of the pressure containment and the structural support. When you look at modern spacesuits, holy cow, are these complex. I encourage you to Google it. We'll probably have some cool art to go with this episode, but many interesting layers going on.
Yeah, and a lot of bespoke pieces being made. I saw that the gloves they do three-dimensional scans of the astronaut's hands so that they can try to maximize for dexterity by
Dude, it's so bad.
Conforming to it.
Because the way that they pressurize these things, so you've got a pressurized suit, and so that fabric becomes rigid because you've got this 14 layers of fabric and you pressurize the inside. Now when you try and actually bend that, when you try and grab something, you're pushing really hard on a suit actually. You're pressing with a lot of pressure and friction. It's actually not uncommon. It's fairly common for astronauts to lose fingernails. They delaminate from the pressure inside these gloves, especially bigger astronauts, bigger hands. Not something I'd ever considered.
That's ridiculous. I had to buy some gloves this winter, and it was actually a hassle trying to find something that's the right size. I thought that finding the right size clothing was a disaster, but gloves, it's
even harder.
Yeah, this is a medium glove. It's what does that mean? Sometimes they give a palm dimension, but otherwise not. Something that's really interesting is the current sort of spacesuit, the Axiom spaces. They call it the Ax-Emu.
Uh-huh.
Maybe they call it something different. That's just my read of it. They actually had a collaboration with Prada to bring their expertise in terms of materials and sewing methods, because trying to join all of these different materials together and how to find the best weave beyond just what you could buy off the shelf really mattered.
Kate, I'm kind of curious, you did sort of textiles and design. When you talk about many different multiple layers coming together, how would you tackle this problem from sort of your training and background?
Oh, I can imagine it would be extremely difficult. I mean, I never was that good at fashion design. I think, again, I think I mentioned earlier, the 2D to 3D element of making anything like that is actually just such a challenge in itself. So, yeah, and then having that many layers to contend with I'm not surprised they got some fashion people on board.
Well, yeah, especially it's like you're trying to create a sealed suit. But every sew, like every needle point, that's a point of entry or a point of failure. Yeah. I feel like that would be just, when you're preparing for cold weather, usually you want to kind of offset your layers. So like some layers you're tucking in, some you're pulling out so that air has to kind of travel through a difficult path to actually get to your skin. And I have to imagine it's probably something similar. It's just like a maze of stitches such that the actual path distance between you and the vacuum of space is maximized.
Well, that's actually something they come up with. With the insulation, they basically make the clothing kind of like a thermos. A thermos works because it has like a vacuum. And if it's thin enough, then you don't get convection. In space, you don't have convection. In fact, you have radiation and you have conduction. So the way that they manage insulation is with many layers of basically Dacron, which is providing the spacing. It's like a polyester. But then you've got like these mylar reflective layers. And if you build up enough of these, it actually serves as a pretty good little insulator thermos that you build around yourself. And so managing heat, they actually have liquid cooling running through these, which I think is so cool. There's actually, what's it made of? It says ethyl vinyl acetate water transport tubing. It just looks like a little like hospital tubing, basically running through the suit to help manage your temperature. The name of the system is Liquid Cooling Ventilation Garment, LCVG. That's going to be close to your inner layer. And then outside of that comes the bladder, which is basically the same thing as they did in the 70s. They're using a urethane-coated nylon. And outside of that comes the radiation resistance, the micrometeoroid. And basically, it's just a bunch of layers of aluminized mylar with an outer protective layer.
Yeah, and those basically work the same way as our antennas that we were discussing at the beginning of this episode. They're reflecting RF, not nearly at the same wavelength as these antennas for communications, but body heat.
So something really cool I learned when I was getting ready for this episode is, in atmosphere, if you're at the sea level, then the ocean of air above you is exerting pressure on you, something I don't think a lot of our students think about. Like you're literally like being squeezed on by all the air around you. And the pressure that we experience at one atmosphere is about 15 psi, 14.7. So I would have assumed that people in space are at that same pressure. And in the space station, they are, right? And they model the Earth's atmosphere in the space station. In other words, mostly nitrogen, right, 70 or whatever percent. But when they go out and do these EVAs, these spacewalks in their suit, they do not take it up to 1 atmosphere of pressure. They are way lower. They go down to 4.3 psi. So that's 3 times lower. That's like being up, I don't know what it is on, Everest, but it's like significantly lower pressure. And the reason they do that is because if you fully inflated this suit at 15 psi, it would not be mobile. It would just be like poof.
Probably be like the kid in Christmas Story.
Yeah, you wouldn't be able to, let alone flex your fingers, give me a break. You wouldn't be able to move your arms. Like it'd be very, very rigid, even with the restraining layer. So instead, they lower it. They air it down to 4.3 psi, and the principle is so clever. In Earth's atmosphere, we have 4.3 psi of oxygen on us because most of it's nitrogen, but we have 4.3 psi of oxygen. So they basically match it. They said, okay, what if you pressurize the suit with pure oxygen now and you take it up to that lower pressure? This allows it to be much more mobile, which is great, but it comes with some serious challenges. Think about it. You're now going to be breathing pure oxygen. That's like what you do when you go scuba diving. And when you do that, you run into this problem of the bends, right? The idea is that if you've been breathing nitrogen, right, in air, and then you go down in pressure, that gets pressurized, so it's going to dissolve in your blood. If you then start to come up and you're going up in pressure, that dissolved nitrogen is going to come out rapidly and it can form little bubbles, which can cause, oh my gosh, all sorts of problems. It causes joint pain. It can cause neurological damage. It can actually be fatal, the embolisms it causes. So if you have people that are in the space station breathing nitrogen, then you put them in a space suit, that they could get the bends basically because it's pure oxygen environment. So it's really clever when they go out and do a spacewalk ahead of time. They actually do a pre-breathing of pure oxygen for several hours to get the nitrogen out of their body to avoid getting the bends before they go in these spacesuits. How cool is that? It essentially flushes the nitrogen out of their bloodstream.
Another big challenge that you kind of mentioned was this debris that's out in space, these like tiny little particles that are moving really quickly. In the original Apollo missions, they found that even after just like a couple hours, like the spacesuits were being rapidly deteriorated by these. And what makes it worse, it's not really even just the speed, but there's no moisture in the air there, and so they actually don't have any way to erode and become more spherical. So they're actually really sharp. These are effectively like needles, like rock needles flying around.
The astronauts call them like glass powder. In fact, dust mitigation, lunar dust will be like one of the big challenges from a material science perspective that we're going to have to figure out as we move towards next generation space suits, Artemis or Mars or whatever. Because yeah, you're right. There's like tiny little needles and they just absolutely wreck everything. In terms of micrometeoroid shielding, there's some cool technology developed in the 40s. It's a basic principle that we understand today. Like even like bulletproof vessels today, you have like a hard layer which causes the object to shatter, and then you have a ductile layer behind it that is tough and can sort of flex to catch it. That's basically what they do. They have like a bumper layer, some standoff distance, and then the catcher's mitt, the rear wall. And if you have multiple materials, one that's hard and one that's flexible, that can manage the impact of these tiny particles. And they use lots of stuff. They use liquid crystal polymer, actually. They've got which is high strength, got good creep resistance. And then you've got the ceramic fiber, which is really, the more rigid layer.
Yeah, fibers are really the kind of the name of the game here in terms of just their strength to weight ratio for shielding. Like they still use those metal bumpers. Like you said, it's usually aluminum. It's called a Whipple shield to provide some initial splitting of that degree. But I think they, on board the space station right now, in terms of textile shielding, I think they have somewhere around 25 metric tons of textile materials just for shielding. And the textiles are supposed to be the light ones. So you can only imagine how heavy that would be if this had to be entirely metal. A big challenge with these micrometeoroids is that we currently don't even have a way to test it in what a lot of these things actually experience. Right now, our primarily experimental tool, these like gas guns, and they can get something up to about 7 or 8 kilometers per second. But when you consider that debris in low Earth orbit is roughly 10 to 15 kilometers per second, this means that we can really only achieve about 40% of the total impact conditions that something will experience. And so this forces us to extrapolate. But now we have to basically design for impacts that we can't even test.
Holy smokes. And I know we're getting long on this, so I'll just say like some of the cool things coming down the line. I encourage listeners to check out like something like the MIT biosuit. The idea behind these next generation spacesuits is instead of having a bubble of gas that you're inside of, which is like this balloon that has to be restrained, what if you provided pressure directly to your body? They call these mechanical counter pressure suits. Think of like elastic bands. If you had a fabric that was really elastic and it was squeezing and compressing your skin directly, then that pressure would prevent the fluids in your body from boiling in the vacuum of space. So there's lots of potential benefits. Way more mobile, way lower bulk, much less weight, and it could be much more like easier bending. But the real challenge here is that having the sort of balloon of gas keeps you under constant pressure everywhere. If you are relying on an elastic fabric to do that, then it's really hard to achieve uniform pressure. And you really want like a nice even 4 psi across your whole body so you don't get local swelling. And the other challenge is, think how hard these would be get into. This would be very tight. Like I was in California and we would go put our wetsuits on to go surfing, and just getting a wetsuit on was hard. Now imagine one that's squeezing you at the same 4 psi all across your body over every square inch of you is going to be very hard to get on and off. And then the last thing is complex body shapes. Means that designing this is going to be a bespoke engineering problem. It's going to be very difficult to get it to be a perfect fit for every body shape.
Something I was going to mention is, when we were talking about kind of things damaging fabrics and stuff, is even when I'm working, I have to think about I remember you saying something about the needle, it's like needles poking through. It's like literally every every time I pass a needle through a fabric, I have to consider, what that's going to do to the weave structure. Like, thinner needles kind of don't have as much impact, but if you need to do a bigger stitch or for whatever you're doing, if you're punching a hole through something, you've got to make sure that your structure isn't just going to start unraveling if you're kind of changing it and taking something in and out of it. It's really interesting being able to use that knowledge. I mean, it comes from years of me staring at my loom and looking at my woven fabric. Like I almost like immediately zoom in with my vision to both knitted and woven fabrics to imagine what's going to happen to it if I do this.
So cool. Well, Kate, you're amazing. Thank you for joining us and telling us about space textiles. You've sent me down a rabbit hole of really interesting topics, and realistically, we'll probably have a follow-up episode because we did not even come close to covering everything. It's been fun to chat with you. Best of luck to you in the research you're doing there. And how cool to know that some knitted textiles are up there maybe facilitating this conversation that we're having even right now. Like, how cool is that?
Very cool.
Hey, we want to remind our listeners that today's episode is sponsored by Momentum Transfer. I've said it before, but having access to synchrotron data for powder X-ray diffraction is an absolute game changer. The resolution and intensity allows you to access information about your materials that are just not accessible with lab X-ray. And now with this company, you can get access to that synchrotron data without time-consuming proposals, waiting for them to get approved, sending somebody to go actually do the measurements. It's an absolute game changer. I love their business model. I hope you'll take advantage of it. And they've made it possible. In fact, if you go to momentum-transfer.com and you sign up, then you'll be able to get total scattering and PXRD measurements for 5 samples for free. You just can't beat that. So check them out.
The Materialism podcast is also sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of the fantastic articles that they've published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
And then lastly, thanks to the people that make the music for the show. Thanks for the listeners who reach out and suggest episodes. You can get a hold of us. We are materialism.podcast@gmail.com or the @materialism.podcast on Instagram or pretty much wherever else. We would love to hear what you want to hear next. So drop a comment, whether this is on Spotify or on YouTube or wherever you're listening to this. Leave a comment. I try and get to all of those. Send us a message on Instagram. We try and respond to everything because we appreciate our listeners. We love that you're out there. And with that said, we will wrap it up. See you, everybody.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.